Now let's look at work and kinetic friction. Bubba the Eskimo pulls a 40 kilogram sled with a constant force of 120 newtons at an angle of 30 degrees above the horizontal. If the coefficient of kinetic friction between the sled and the snow is mu sub k is 0.2, how much work did Bubba do on the sled after he's pulled a distance of 10 meters? Part B, how much work did friction do on the sled in the same distance? We will use our imagination and pretend that this is a sled and that this is snow. The givens. We know that the mass of the sled is 40 kilograms. We know that the magnitude of the pulling force is 120 newtons. We know that the angle theta between the pulling force and the horizontal is 30 degrees. Since the sled is moving over a horizontal surface, it is moving neither upwards nor downwards, and so its acceleration in the y direction is 0. Its velocity in the y direction is also 0. The displacement is 10 meters, and the coefficient of kinetic friction is 0.2. The forces on the crate are the pulling force, the frictional force between the bottom of the sled and the snow, the weight force, and the normal force acting vertically by the snow on the sled. We collapse the sled to a particle at its center of gravity as usual. We place the tails of all the force vectors at the center of gravity, a particle at the center of gravity. We then resolve all off-axis forces, which in this case is only the pulling force, into x and y components. The final step for our force diagram is to draw components only. Along the x-axis, we have the x component of the pulling force acting in the positive x-axis direction, opposed by the frictional force acting along the negative x-axis. For vertical forces, the only downward force is that of the weight. Upward forces are the y component of the pulling force, F p sub y, as well as the normal force. We see that in this case, the normal force will not be in magnitude equal to the weight. The unknown. For part A, we would like to know the work by Bubba on the sled after he's pulled it a distance of 10 meters. Bubba is exerting this pull, so we need the work by the pulling force F sub p. The equation for part A. Since the pulling force is not along the direction of the displacement, our equation for work is magnitude of the force doing the work times the displacement magnitude times the cosine of theta, where theta is the angle between the force vector and the displacement vector. The work by F sub p is magnitude of the pulling force F sub p times magnitude of the displacement S times the cosine of theta. Substitute and solve. The work by F sub p is the magnitude of the pulling force is 120 newtons. We write that down. The magnitude of the displacement is 10 meters. We write that. And times the cosine of 30 degrees. Evaluating this, we get 1039 newtons times meters. We round to 3 significant figures, and this gives us that the work by the pulling force, or by Bubba, is 1040 joules, since a newton times a meter is a joule. The unknown for part B, to find the work by the frictional force. Since the frictional force is not in the direction of the displacement, our formula is that the work by the frictional force is the magnitude of the frictional force times the magnitude of the displacement times the cosine of theta. To substitute in, we don't know the frictional force. We do know the magnitude of the displacement is 10 meters. We do know that theta is 180 degrees. We have to now write down the formula for the force of kinetic friction. To find the magnitude of the frictional force, we write down the formula for friction. The kinetic friction force is the coefficient of kinetic friction, mu sub k, times the normal force. We are given the coefficient of kinetic friction is 0.2. However, we do not know the normal force. We must therefore use Newton's laws to find the normal force. We see that along the y-axis, the sled is at rest. Therefore, all the y forces must be balanced. Since the velocity is constant at 0 along the y-axis, we write Newton's first law along the y-axis. Net force along the y-axis is 0. We go to our force diagram to see what the net force is. The net force is the normal force plus the y component of the pulling force. These are both positive, so we write plus signs for those, minus or plus and minus the magnitude of the weight force. These sum to 0. Solving algebraically for the normal force, we get that it is the weight minus F p sub y. We substitute in 40 kilograms times 9.8 meters per second. For F p sub y, we have minus 120 newtons, which is the magnitude of the pulling force, but F p sub y is the opposite side, and so it's hypotenuse, or F sub p magnitude, times the sine of 30 degrees. So we write minus 120 newtons times the sine of 30 degrees. Evaluating, we get that the normal force is 332.0 newtons. We now have enough information to solve the problem. We substitute in for the frictional force 332 newtons. Then the work by the frictional force becomes the magnitude of the frictional force, or 332 newtons, times the magnitude of the displacement, or 10 meters, times the cosine of 180 degrees. The cosine of 180 degrees is minus 1, so this is a negative work. Since a newton times a meter is a joule, our final answer is that the work by the frictional force is a negative 3320 joules.